Okay, so here's an ease program that actually identifies these eigenvalues. So if you look at what I've done here, these are just some inputs. They don't matter too much. This is my duplicate loop where I have programmed the eigen condition. So this condition right here is hopefully exactly equal to, let's go back to here. Oops. Exactly equal to this condition right here. So I'm trying to find the roots of this, and of course ease is good at solving implicit equations, so I can just program it, as it stands here, and that's what I've done here, right? And if I just solve doing nothing else, then what ease is going to do is find 11 solutions to this equation. But because I've given ease no guidance as to where to go look for those solutions, they're probably all going to be the same solution, and they're all going to be, some solution that's close to whatever the guess value is for lambda times w. So if we solve right now and look at it, you can see that it found basically, I think this is probably the second eigenvalue over and over and over again, which isn't very handy. What I'd like it to do is find the first eigenvalue and then the second one and the third one and so forth. So what I have to do is tell ease where to look for these eigenvalues, right? So that's where knowing these ranges comes into play, right? Because if you look at what ease does, if you go to the variable information window, which you can get to with this button right here, or with options variable information, you can see that every single variable in the ease equation set has a guess value, and you also have the ability to set a lower and an upper bound on the equation. So this is what we're trying to find, is this lambda w. If I click show array variables, you'll see that there's 11 of them, right? So there's, where am I at here? There's 11 of these lambda w's, right? Each of them has a guess value. They're all the same because they haven't done anything. Each of them has a lower limit and an upper limit. And right now, you can go from minus infinity to infinity. So what I need to do is, in another set of arrays, specify what the lower limit is for every one of those eigenvalues, and what the upper limit is, and what the guess value is. And then I have to take this information in these three arrays and put it into the variable information window for that variable, or that array lambda w. So that's what I'm going to do now, right? I'll solve, so I make sure that those ranges are specified now, right? This is basically saying, I want to find an eigenvalue between this value and this value, and then I want to find the next one between this value and this value, and then the guess value is just halfway between these, right? Then I go to the variable information window, and I make sure that this is deselected, so I've collapsed the entire array into one variable here. And then here I'm just going to type in, make sure I get this right. I guess this is going to be guess with square brackets, and here I'm going to do lower limit with square brackets, and here I'm going to do upper limit with square brackets. So what I've done here is I've said, for each of these elements in this array, the guess value should be the corresponding element in the array guess. The lower limit should be the corresponding element in the array lower limit, and the upper limit should be the corresponding array in the array upper limit, right? So we'll hit apply and OK. And if I solve again now, what I find is that ease is now identifying the eigenvalue that exists in each one of these ranges. So it's faithfully now identifying the first 11 eigenvalues. And if I change n term to something bigger, it'll continue to identify eigenvalues farther and farther out, right? So that's one way to find all of your eigenvalues. And again, in every software there's going to be something like that, and you just have to implement that. Okay, so that is the solution to our eigen problem then, right? At this point I have I have the functions, and I also have all these eigenvalues, right? So that's only a little bit harder than it was before. Step 4 is come back and solve the non-homogeneous problem now for every eigenvalue. So here's the non-homogeneous ODE. All these eigenvalues are defined by the roots of this equation, but I can find as many as you'd like. This is solved by Koch and Cinch, same as it was before. The temperature solution then for every eigenvalue is just theta x times theta y. So it's the sine times this thing right here. So I get this guy here, same as I did before. And then step 6 is assemble all of the solutions. So get your series solution. So I'm just going to add all these up, which I've done here. Right. So thinking back to what this does now, if I go back, this solution, as far as I have it so far, this solution satisfies this differential equation, it satisfies this boundary condition, and it satisfies this boundary condition, right? So the last thing I got to make it do is satisfy the two boundary conditions in the non-homogeneous direction, and that is step 7. So let's go to step 7. Enforce the boundary conditions in the non-homogeneous direction, so that's the heat flux at the bottom, and then the specified temperature at the top. So let's see. Previously, one of these two boundary conditions was homogeneous, right? In the first problem we did, and that made it really easy to figure out how to satisfy that boundary condition. We didn't have to use the orthogonality of the eigenfunctions. We could just plug it in and look at it and go, oh, okay, all the C3s had to be 0 or something like that, right? In this case, neither one of these are homogeneous. So what that means is I'm going to have to use the orthogonality of the eigenfunctions twice. So I just take this solution here, substitute it into here, and that gives me this equation here, right? I have the heat flux is minus K times, I just took the derivative of this thing with respect to Y and evaluated it at Y equals 0. So that's why the Koch became a Cinch, and the Cinch became a Koch. Cinch of 0 is 0, Koch of 0 is 1, so that becomes this right here, right? And this is not an equation where I look at it and go, well, this would be satisfied if all of my C4s are 0 or something like that, right? This is, again, one equation in an infinite number of unknowns. So I have to remember what the orthogonality of these eigenfunctions allows me to do, right? If I take any of these sine functions and multiply it by a different sine function and integrate from 0 to w, I'm going to get 0. So I take this entire equation and I multiply it by sine of lambda j times x, both sides, and then I integrate both sides from 0 to w, and I get this equation here, right? So on this side I get the heat flux times the integral of the sine function, and then on this side all of those integrals of the product of two eigenfunctions integrate to 0 except for the one time where I is equal to j, right? So sine squared. So all I'm left with on this side is this part of the equation. So I have an equation here that I can use to get every one of my C4s. So at this point, all of my C4s are known, and I've satisfied this boundary condition. And I have one more boundary condition to satisfy, and that's this one here. So I take this equation. I still don't know my C3s. I know all of my C4s. I plug it into this guy here, and that gives me this here. And I've plugged in y equals h, and I've set it equal to th minus t infinity. Again, this is not something that can obviously be satisfied easily. Instead, I have to recognize that I want to take this series and turn it into only one term. And the way I do that is I multiply both sides by the eigenfunction, integrate from 0 to w, and there's only going to be one term left on this left side. Right? So that's what I've done here. All of these terms go away, and I'm integrating sine squared of lambda ix, and then whatever I do to this side, I also have to do to this side. So I'm going to integrate, sine of lambda ix dx. So here's another equation, right? I have to do these two integrals, but that's not too hard. I already know all my C4s, so this equation is going to give me all my C3s. So this gives me, at this point, everything I need to implement my solution. Right? Here's my solution. I know all of my C3s from this equation. I know all of my C4s from this equation, right? And I know all my my eigenvalues by finding the repeated roots of this equation. And that's it. Right? I can implement this and look at it and do whatever I want with it. So that's about as hard as we're going to get in this class anyway. Right? This is now to the point where you can solve pretty sophisticated problems, but actually not every problem, right? So we got a little bit lucky in this problem back when we started, in that when I did the transformation of solving this problem in terms of t minus t infinity, so in terms of theta, I managed to transform both this boundary condition and this boundary condition into homogeneous boundary conditions. And that's not always going to be the case. Right? There's going to be times where no transformation is going to give you two boundary conditions that are homogeneous in one direction. And that's where you have no choice but to resort to superposition. Right? So that's the last thing we'll talk about is superposition.